let me start by saying a little bit about my background, because it's a bit different from the background of most of the people here in the audience, perhaps. Okay, where is it? Yes, there. So I don't work for a company, and I don't work with customers, but I do get paid to play with Clojure, so that's kind of a sweet position to be in. And so how you can manage this for yourself is to start working for a university, okay? So I'm affiliated with the Dutch Open University, which is a university that specializes in distance education already before the pandemic, so that was, well, I wouldn't say the pandemic was convenient for us, but it was at least something that we were already kind of used to. And I'm also affiliated with Centrum Wiskunde en Informatica, which is the Dutch National Research Institute for Computer Science and Mathematics. And it's actually also here in Amsterdam. So most of the time I'm here at CWI, where my main desk is, if you will. Yeah, so I say I get to play with Clojure. When I show these slides to the marketing people in our institute, they say, no, you shouldn't say that. You should say you do research, right? Okay, so I do research using Clojure, but it's more or less, at the end of the day, it's more or less the same thing. Okay, so what I want to talk about today is core.async, and in particular, an automated correctness analysis for core.async. And I imagine that maybe not every one of you has seen or used core.async before, or maybe a long time ago. So should I stand in one place? Is it better if I stand?
No, this is fine.
Okay. Sorry about that, guys. Core.async. So core.async is a library for Clojure, obviously, and it was introduced some 10 years ago by a blog post of Rich Hickey himself. And so just to introduce this library, I want to mention a few of the statements that Rich makes. So first, one thing that he says is, well, the objectives of this library are to build upon the work done on CSP. Okay, now CSP may sound maybe foreign to many of you. It should perhaps, because CSP is somehow a kind of a mathematical model of concurrent programs. Okay, now that sounds kind of complicated, and yes, when you look at all the theory that underlies CSP, it is really quite complicated, so I don't want to go in there. I just want to mention two, let's say, elements or ingredients of CSP that are relevant for core.async. The first one is that CSP, when you reason about your concurrent programs in terms of CSP, you have processes, okay, and you have channels between the processes through which they can exchange messages, and that's it. That's all you need to know for this presentation to understand core.async. So what this core.async library does, it sort of tries to expose this model, right, to programmers in Clojure so that they can build their concurrent programs in terms of processes and channels between them. So you have functions and you have macros that support this kind of stuff. That's in a very tiny nutshell what core.async is about. So Rich explained this and the rationale and the usage of this library very nicely in this blog post. And then towards the end, he makes two interesting statements. So the first statement he makes, maybe I should put this a bit down. Yeah. The first statement he makes is that CSP proper is amenable to automated correctness analysis, but no work has been done on that front for core.async as yet. Okay, this was 2013. So fast forward to 2018. Okay, so I work in a university, and so we have students. Okay, and these students at some point they need to graduate. And when they graduate, they need to be supervised by someone from the university with their graduation project. And so late 2018, one of our students comes to me. He says, okay, I'm ready to start my graduation project, and I want to do it somehow at the intersection of your research area, which is concurrent programming, my research area, and Clojure, because I'm really excited about Clojure. And at the time, I had heard about Clojure, but I hadn't really used it yet. Okay, so I was really a Clojure novice, so to speak. But he was really, eager to do this, and so we said, okay, let's try to do that. Let's try to find a kind of a small research project based on which you can graduate. Okay, and so we looked at the literature, we looked at what existed at the time, and we also came across this blog post, and we read this statement, and then we looked around to find libraries where you have this automated correctness analysis, because it was 5 years later, right? We couldn't find any. Okay, and so the graduation project of this student, he ultimately became, the development of this kind of automated correctness technology. Okay, and that's what I want to talk about today. So I would say that from, let's say, academic or, scientific perspective, the project of the student was really successful in terms of publications, right? That's what I actually get paid for. So at the end of the day, he and also other students later on worked on this, and we published about this, and we were very happy, and I got my paycheck, and okay, everything was fine. But wouldn't be the first time that people in a university invent something that they're very excited about, but that has no practical relevance whatsoever. Right? This happens really all the time, even more often than you can conceive. So basically what I'm doing here today is I'm really looking for feedback. Okay? So I think that now, again, a few years later, we are at the stage where we ourselves understand sufficiently well what we actually is that we've been doing, so that we can communicate to, let's say, normal people. So I just want to show you what we've done, and it would be great if you say, oh, this is great, we really want to use this. It would be even better if you said, no, this is totally useless, you should do something else, right? Because then we can sort of steer our own research towards something that people can actually use in practice. Okay? So that's the plan. And so the rest of the presentation consists of 3 parts. Okay? In the first part, I want to just very quickly give a sort of a crash course on core async, so that we're all on the same page. Then in the second part, I'll show you a few of the mistakes that are very easy to make when you use this core async library. And then in the third part, I'll show you more about the particular techniques that we've developed. Well, not really to avoid the mistakes, but at least to detect the bugs and the errors that are the result of the mistakes, so you can do something about them. Right? So it's for debugging. All right, so what I want to do is I want to do this based on an existing very small example in core async that I didn't invent, but this was also presented in a blog post by Alex Miller. It's rock, paper, scissors in core async, and it's very simple. Okay, so on the next slide I will show you the code, but first let me sort of try to describe the architecture, if you will, of this thing, which is shown now here. Right? So in this program, we'll have 4 processes: main, judge, Alice, and Bob, where Alice and Bob are the players of rock, paper, scissors. I'm just going to assume that everybody knows rock, paper, scissors, right? And so what happens is that Alice and Bob, they randomly pick a move, right? Rock, paper, or scissors, and then they send this move to the judge, okay? And so then the judge, he knows the rules, presumably, and so the judge can determine who is the winner, and then finally it will send the name of the winner to the main thread, and then the main process will print it to the command line or something along those lines. Okay, so what does that look like in the code? I want to remove this pointer because it irritates me. Like this, okay. Okay, so let's first define a bunch of, let's say, domain concepts for rock, paper, scissors. It's all really simple. So we have moves, rock, paper, and scissors. We have a map that defines which move beats which other move. Okay. Then we have a function to compute the winner. So the function takes 2 arguments, each of which is a pair, the name of the player and the move that the player has played. And so if both the moves are the same, then of course we have a draw, so nobody wins. But if the moves are not the same, then you can very easily compute the winner. Okay, so that's what the function does. Fair enough. Then what else do we need? Well, we need something to report the winner. So this is what the main process is going to call. It is just a wrapper around print line, so that's not really interesting. Okay, so what I'm going to show you here on the right panel now is basically 2 functions. Okay, and the idea of these functions is that they're going to create the processes and create the channels that we need in this rock, paper, scissors program. So one of the functions is for the creation of player processes. Okay, and we'll use a single function to create 2 processes because they're essentially the same, right? And the other function will be to create the judge process. And I'll assume that the main process is just a process that's always there. Okay, so that's easy. We don't need to explicitly spawn that. And what we'll see also is that the internal structure of these 2 functions is basically the same. So I will first show you the simpler one, which is for the players, and then I'll show you the more complicated one, which is still not really complicated, but still a bit more complicated for the judge. Okay? So, okay, let's go there. So first, we need to load the core async library. Okay, we can all do that. Now here's the function for creating the player thread. Okay? And so what happens is the following. First, what we do is we create a new channel. So this chan function comes from core async, and it allows you to create, in this case, a channel without a buffer. Okay, a buffer, an unbuffered channel, which means that when you do a send and a receive on this channel, right? Both the sender and the receiver need to be there at the same time. Right? There's no buffer to store the message while it is in transit, okay? So we create this channel, then we spawn the thread, and this is in some sense an asynchronous operation because, well, when you create the thread and you start the thread, then this thread is going to execute asynchronously, so that's the body of the thread. Okay? And so what you can do after spawning the thread, right, irrespective of what the thread is actually doing, is immediately return a reference to this channel. And so what happens here essentially is that this channel, right, it is supposed to be used as the outgoing channel of the player process, right? And so inside the body of the thread, right, the channel is accessible and it can perform send operations, right? That's what we want. But of course, we also need someone to listen to the thread. And that is something that we can achieve by returning the reference to this channel. So this channel is now a shared object, right? And so the environment of the thread, if you will, is now able to perform receive operations. We will see exactly how this works later on. Okay, so the only thing I need to do now is also, show you the body, and the body is very simple. So what we do is we call this function, which is sending in core.async. We send it through this outgoing channel, fine, and what we send is this message, and this message is just a pair, namely the name and a random move. Okay, so that's all that the player does. Now I already said that this judge function is going to be very similar in structure, at least, as the player function, and I think it is, right? So here we see it. Again, it creates its own outgoing channel, it spawns this asynchronous thread, it returns the reference to the channel, so that's all the same. The only thing that's really different is, of course, the body of the process. What is interesting here is that the arguments of this judge function, they are supposed to be references to the outgoing channel of the player, right? So then in the body of the judge, right, you can perform this function, which is receive. And so you can receive from the channel from player 1, you receive from the channel from player 2, then you have two moves, right? You can pass the moves to this winner function that we defined here, and then after calling this function, you get the name of the winner, and that's then a message, so to speak, that you can send through your own outgoing channel. Okay? So basically, that's all we need, except that we also need to define, of course, this main process. I'll show it here, but instead of explaining this code directly, let me try to do it more step by step, okay? And I'll also draw a picture just to make it very clear. So initially, we have only the main process, okay? And so what the main process does is it executes this code. By the way, I'm using the words process and thread interchangeably in this presentation because process is CSP terminology, but thread is obviously core.async terminology. So in this, it doesn't really matter in this presentation, but yeah, just to be clear. Where was I? Okay, so we have this main process or thread, whatever. First thing it does is it calls randPlayer for Alice, right? So it spawns Alice, and what happens when this function returns is that we get this reference to the outgoing channel of Alice. And so in this picture, you can think of this as, Alice is a thread that now exists, right? It is actually executing something. But the outgoing channel of Alice, it's in some sense dangling, right? Because we know that Alice is going to perform the send, but we don't know yet who's going to perform the receive. Okay? Now, similarly, we can do this for Bob, right? And then once Alice and Bob are spawned, then the main thread also can spawn the judge, right? And so the judge gets as arguments the references to X and Y, or the references to the channels. And so you can think of this as sort of that these channels are now connected to the judge, and the judge receives from these channels. And well, finally, the judge sends this message to the main thread, and the main thread then performs the reciprocal receive operation on this channel. Okay? And then if you execute all of this, then, well, hopefully you can simulate rock, paper, scissors. So let's see if this works. Right. Oh, this is very small. Okay. I don't know why this is so small. So the resolution is at least very, I can hardly see this. Oh, okay, wait. Oh. Appearance, enter presentation mode again. No, it's just, yes. Okay, much better. Okay, so what do we have here? Oh, this is just these domain concepts, right? This is exactly the same as what I showed on the slide, but just to show you that it really exists also on my PC. Then, okay. right? Is it big enough? Should be, right? Okay, so here we have the same code as on the slide again. So we have here for this random player, okay? We have the code for the judge. That's fine as well. Now, here we have the code for the main thread. And so I wrapped it in a test to be able to execute it easily. So, hopefully something. Ah, Bob wins. Okay, perfect. Can we do it again? See if someone else wins. No one wins. Okay, so this really seems to work. Very good. Okay, so this was sort of the core async crash course. Okay. Let me now talk about some of the mistakes that are very easy to make when you write this kind of core async code. And I want to discuss two classes of mistakes that we have here. So the first class of mistakes is mistakes that concern somehow the wiring of the application, in the sense that of course, there's some intention behind the channels that you create and the processes that are supposed to use them. But if you make a mistake in actually writing the code, then all things can go wrong. So here, the mistake is that we have this channel Z, which is the outgoing channel from the judge, right? But apparently, the main thread tries to receive something from channel Y. And in the picture, it looks really strange, but the idea here is now sort of that we have two processes, main and judge, that both are trying to receive the message from Bob. But it's important to realize that Bob will send only one message, right? So main and judge, they are sort of engaged in a kind of competition. We can think of it as a race, not unlike data races that you have in classical shared memory concurrent programming. Only in this case, they're not really racing for shared data, they're racing for access to the shared channel, right? They both want to receive from Bob. Now, depending on who wins the race, right, two different things can go wrong. And instead of trying to explain it first, maybe I can show you just the demo again to see what kind of bad behavior we can get here. So this is a second test where indeed we made this mistake. So we're listening to Y, and Z is unused. IntelliJ tells me already this, but okay. Okay, we do get some output. It's a bit small, but doesn't matter. So the output that we get is Bob Scissors wins. Okay. Now, first thing that we can notice is that the formatting is not really right, and this is very suspicious, right? It tells us that, you know, the type of the message or the type of the data that we're printing here, so the actual type is not really the expected type. And the thing that really goes wrong here is that main, in this case, wins the race. And so main received the message from Bob, which was intended to be received by judge, but main receives it and thinks it is the message that it received from judge. Right? So it expects that the type of the message is just a string, namely the name of the winner, and that's, you know, it just blindly prints this. But this is not at all what we intended to happen. Right? So one of the errors that we can get because we made this wiring mistake is that you know, the outcome of the computation is just wrong. Right? It has a wrong type. So this is when when main wins the race. But we can also have the situation where judge wins the race. But because of, you know, non-deterministic scheduling and all that kind of stuff, I need to somehow force this to happen here. And I do this just by delaying the main thread for 500 milliseconds, so judge can win the race. Okay. And so yes, I don't know if it's visible, but what we see here is that this test is actually running, and it's still running, and it will run actually forever. Okay, because the error that we're seeing here is actually a deadlock. Right. Some of the processes have gotten stuck. So what happens in this case is that because judge wins the race, right, judge receives the message from Bob. Okay, that's fine. It can compute the winner, and it tries to send this winner to main. But main is listening to the wrong channel. And so main still expects to receive this message that Bob is never going to send again. Right? So main gets stuck listening to one channel. And actually, the judge also gets stuck because he wants to send this message to main, but main is listening to the wrong channel. Right? So in this case, we have two processes that have gotten stuck. Okay, so, well, maybe I can stop this because it's not really relevant. So, long story short, there are two kind of problems we can get here. It's deadlock, or we can get the wrong output in the sense that the type of the output that of the actual output is not the expected output, okay? And this is only when we listen to the wrong channel, right? Even if we get the wiring right, so even if we listen to all the right channels at the same time, there's another class of mistakes that we can make. And this is just, you know, that we get the implementation of the processes wrong. So here, I have another version of the judge, which is, let's say, an unfair version. And it's unfair because it still receives this message from player 1, but then it completely ignores player 2. It just extracts the name from the message and will always send the name of player 1 to the main thread. And so, well, clearly this is not what we would expect of a fair judge. When we try to execute this, something will go wrong as well. So here we redefine the judge. That's fine. Let me just run this test. Like this. Okay. And so what we get in this case, well, we can of course try to reason about this. We get Alice wins. Okay. So I think one of the main problems here is actually that this output, based on this output, we cannot tell if something went wrong inside the processes, right? It's just, it looks okay. It is possible that Alice wins, but the computation inside the judge is really wrong. And we would like to catch these kinds of mistakes as well. Okay, so we have these three actually, classes of errors that we can now get. Deadlock, wrong output of the type, wrong output of the actual value, okay? Now, if we zoom out a little bit, sort of from these classes of errors, then I think an interesting observation, or an important observation at least, is that there is a kind of a common root cause underlying each of these things, and it is incompliance. Incompliance in this case means that inside our minds, when we write this program, we have somehow a kind of intended communication protocol that the processes should follow. And in this case, it's actually very simple. It's just that Alice sends to judge, Bob sends to judge, judge sends to main. That's the protocol that we want the processes to abide by, and that's what we expect. But in each of these cases, this is not what happens. Okay? And so when I talk about automated correctness analysis for core.async, right, the way to sort of the way in which we operationalize this is that we want to check for compliance. We want to be sure that when we execute a core.async program, that the processes follow the protocol that we have in mind. And if they don't, then we want to get an exception. And we want to get this exception as early as possible so that it's easier to debug. Right? So we want to fail early and we want to fail loudly. Okay? Okay, so that's very nice. I mean, we can all want that, but then the question is, how do you do it? Okay, so we need 4 ingredients for this. Okay? The 0th ingredient is the concurrent program itself. So it's not really an ingredient of the approach, it's just something that we need, hence 0. Okay? The first thing that we add to such a program is what is called instrumentation. And it's basically just a very thin layer around this concurrent program that allows us to observe so-called events of interest that happen in this program when we execute it. Okay? And the events of interest in our case are sends and receives and a few other actions as well. Okay? But this is sort of what we want to observe. You can think of this instrumentation as a kind of fancy runtime logger, if you will. Okay? Now, logging these events is only the first step, of course, because when we know which events have happened in the program, we also need a mechanism to pass judgment, right? To say, okay, these events have been okay, or these were not compliant. And so the second real component that we add is a runtime monitor. Okay? And what this monitor essentially does, or what actually the instrumentation together with the monitor do, is at runtime they sort of communicate with each other in a loop, right? So every time when an event of interest, so a send or a receive, happens or is observed through the instrumentation in the program, the instrumentation asks the monitor if this event is allowed to happen. Okay? If it is allowed to happen, the monitor will say, yes, okay, it's okay, and then the instrumentation is fine. If it's not allowed to happen, then the instrumentation will throw a runtime exception. Okay? That's in a tiny nutshell what is happening. Now that's great or not great, I don't know. That's, I mean, at least how it works. But of course, it is essential in some sense that the monitor, well, it must know what is this intended communication protocol, of course. Otherwise, what is it going to be analyzing? And so the final ingredient that we need is a specification, okay? A specification of the protocol. And the specification language that we implemented for this is basically just a bunch of Clojure macros. And in defining these macros, we drew, a lot of inspiration from regular expressions in spec. Okay, so for instance, this is the specification of the protocol that we've been considering so far. CAT stands for concatenation, so it's just a list of things. And then this arrow notation means a communication of a message from Alice to judge. Okay, so it should be kind of intuitive to write these kinds of specifications. That's at least the intention. Okay. Okay, so suppose that we now start to execute this program. And at some point, Alice and Judge, they want to engage in a communication. Okay, so right before this happens, okay, the instrumentation is already capable of sort of sensing that it is supposed to happen. This sounds a bit, but as if it can predict the future, but in some way the instrumentation can do this. And right before this communication happens, it will instead suspend, in this case, Alice and Judge, right? So this communication is also put temporarily on hold. In the meantime, what happens is this instrumentation asks the monitor, you know, this message from Alice to Judge, is this actually okay? Now the monitor has access to the specification and it can see, yes, the first communication that's supposed to happen, that is indeed this communication. And so it will inform the instrumentation accordingly that yes, this is all fine. And so the instrumentation will then unblock Alice and Judge, right? So their communication can actually happen at this point, and then the program continues. So a little bit later, right, again, something happens. So we have this communication now from Bob to Judge. So again, this instrumentation asks the monitor checks, yes, the next thing that can happen is indeed this thing. So you get this affirmative answer, and well, the execution continues, and then again we have something else, and this is also allowed. And so at the end of the day, when the execution terminates, we have not seen an exception. And then we're very happy because then we can be sure that all the communications that happened during this execution, that they were compliant. Okay, so that's a kind of an assuring thought. Now we've also seen these examples where we do not have this, or where we made a mistake. And so we can also have a look at what happens in those cases. So here we had this wiring mistake. So first we have this communication from Alice to Judge, that's fine. But now at this point two things can happen, right? We either have main that wins the race or Judge that wins the race. And so if main wins the race, so main tries to receive the message from Bob, and then the instrumentation asks the monitor if this is okay. At this point, the monitor will say, no, it's not okay, because I expect a communication from Bob to Judge to happen instead of from Bob to main. So now the monitor says, no, you shouldn't allow this to happen, and the instrumentation says, okay, if I'm not allowed to do this, then I will throw an exception. Okay? So here we have fail early, fail loudly, because right before the moment in which this communication was supposed to happen, we already have this thing. The other thing that could happen was that there was this communication between Bob and Judge. And the interesting thing here is that this is actually allowed by the specification. So the monitor will now say, yes, you can do this. And so the instrumentation will let it happen. But as we've seen in the live demo, at this point you run into a deadlock, right? So that's not very nice. And so what we added to this instrumentation is another mechanism to also try to detect these kinds of deadlocks. So the instrumentation does a bit of bookkeeping, and it knows how many threads there are in total, how many threads have terminated, how many threads are listening to which channels, and is it even possible for those threads to actually satisfy each other's needs. Well, in this case, it's not the case, right? So in this case, the instrumentation is able to pick up this deadlock and throw this runtime exception instead. Okay, we also had this other example with the unfair judge. I will go through this a bit quickly because it's basically the same as what we saw before. So also in this case, we have this runtime exception. Okay, I want to show you this in the live demo. But before I do that, let me first very briefly explain how you can deploy this kind of technology in the existing program. So there are two things that we need to add. We need to add the instrumentation, and we need to add the monitor itself. Okay. And so for the instrumentation, what we do is we say, or what we build is basically a wrapper around the core.async library. And this wrapper, if you use this wrapper, then the idea is every time you try to do a send or a receive, it goes through our wrapper, and then we can sort of, act on this as well. We can log these kinds of events. And so to use this wrapper, or to use this instrumentation, instead of using the standard core.async library, we just ask you to load our own library instead. Okay, so that's kind of simple. But it's not enough, because we also need to know something about the intentions behind the channels, right? So we need to know for each of the channels who is the intended sender, the intended receiver, and the monitor that we'll be using to verify the actions on that channel. Okay, so we need to add a little bit of this kind of configuration information as well. But this is all as far as this instrumentation is concerned. So the large majority of the program remains untouched, right? It should be at least relatively non-invasive to start using this, okay? And in addition, of course, we also need to have this monitor. Well, I've already shown you the specification itself. We have this def session function to also, actually wrap it in a reel or to register it really as a specification. We would love to have called this def protocol, but obviously it was already something else. So we opted here for session, okay? And then we have this monitor function to actually, build a monitor around this specification, okay? And that's all. That's all we need. So let's have a look. All right, this is, okay. So what should we have done? Okay, so we have this here, our own library. We have this own library for writing the specifications, okay. So we have here the specification that we saw before. Well, basically all this code was exactly the same as the code that you saw on the slide. So here we also add this configuration data to the channels. That's all the same. Let's see what happens when we run now this this main thread without, without mistakes. Okay, so okay, maybe it's not so interesting because we don't see anything because nothing is supposed to happen, right? So we do not get any exceptions, and that's intended. So here we have the version of the main program where main is listening to the channel from Bob instead of the outgoing channel of the judge, right? So this is wrong. And so when we try to run this now, we waited for a little bit, and then, oh, boom, we get an exception, okay? So the exact message of the exception doesn't matter so much. It tries to give you some information about why we believe that this was an incompliant behavior, but the details don't matter so much here. So then here we also had this example where so the previous one was where main wins the race. This is the example where judge wins the race, and here we have deadlock, okay? And then finally, did we have something else? Yeah, okay, so we also had this one where we had the dishonest judge, right? And also here now we get this runtime exception, right? So we really get the exceptions when there is incompliant behavior. How am I doing for time? Okay. Okay, so if I were a salesman, which I really am not, but if I were, and I would need to do a sales pitch to try to sell this stuff to you, I think I would focus on the following things, and you will see that I'm not really a salesman. So let me first say something about the fragment of core async that we support, because core async is a relatively, it's not a huge library, but it has many features, and we support only, let's say, a subset of them. But I do think that we have all the core things in place. So we can spawn processes, we have channels, both buffered and unbuffered, okay? We also have timeouts, which are a special kind of channels in core async. And the operations that we can monitor are sends and receives, closing of channels, but also alts. And I haven't talked about alts at all, but it's very important actually in channel-based programming because it allows you to listen to a number of channels at the same time without knowing beforehand which of the channels will actually fire. Okay, and this is very important to support. And it was actually kind of complicated to do that in this setting, but yeah, so we're happy with that. Then the checks that we can do are for deadlocks and for non-compliance, as I showed. And so for non-compliance, the checks are sound and complete, which are sort of technical terms, but it basically means that if you have incompliant behavior, then you get an exception, and if you get an exception, then there must have been incompliant behavior, right? So you do not get false positives, you do not get false negatives, okay? For deadlocks, it's a bit more experimental, and we're only sound, right? Yes. So if we do get an exception, then we can be sure that there was a deadlock, but there's some deadlocks that we miss, right? So in that sense, we're incomplete, okay? Then regarding usability, I would say, okay, so we have this embedded DSL, so it's just Clojure. You don't need to install any separate tools, so that should be, a low barrier to adoption in some sense. And it's also, it's inspired by spec. So people who have used spec before to write regular expressions, this should feel somehow a little bit similar. And something that I didn't show, but that we also have, is that we can check the contents of the messages. Okay, so the specifications I showed so far was this arrow and then the sender and the receiver, but what we can add to this is a third argument that is basically a predicate. okay? And we will call this predicate when at runtime we have access to the actual message that is going through the channel, and if this message violates this predicate, then also we throw a runtime exception. So you can, at a kind of fine-grained level, you can reason about this kind of communication behavior. And I think that the number of code changes that you need are relatively small, right? You need to add some of this configuration data to the channel construction, but other than that, your program remains exactly the same. So that should be okay. Okay, so this is all nice, or it's not nice, I don't know, but there's one important thing that is not yet in my sales pitch on this slide, which is, I think, kind of important, namely performance, okay? We do all this analysis while we're executing the program, so inescapably, we're going to impose some overhead on these runtimes. Now, if this is only a few percent, then maybe it's not so bad. If it's 10 times slower, then probably you don't want to run this in production, okay? So the question is, can we say something meaningful about performance? And so what we did is we had a number of benchmarks to check the performance. And these benchmarks, what was important for us is to not write our own applications, but to pick a third-party benchmark set, so to speak. And so what we did is we took this NAS parallel benchmarks, and this is a benchmark set that is maintained by NASA, the space agency. And it's, these are computational fluid dynamic kernels. Now, even I don't know exactly what it is, but it's some complicated computations. Okay, I wasn't really interested in the computations themselves, but of course in the communication protocol between these things. Okay, and they have names IS, FT, MG, CG. Very meaningless when we just talk about it like this, but just to identify them. So what we did is we took the reference implementations that NASA provides on the website, which are written in Java. Okay. And then we basically stripped them of all the communication code, right, that is in these reference implementations, and we replaced it with operations on core async channels using Java interop. Okay, so in the end we had 2 versions of these programs, and then we ran them on a piece of hardware with enough cores and enough memory and so on. And then we just measured the runtimes, and then we compared the runtimes of these reference implementations with our versions where we do have this runtime verification as well. And then here are the results. What you see on the horizontal axis is the number of processes. Okay, so we were also interested in scalability. And on the vertical axis, you see slowdown of our versions relative to the NASA versions. Okay, and so when you look at these 2 graphs, which are for IS and for FT, whatever that means, if you look at these 2 graphs, right, it's just 2 classes of programs, doesn't matter. Let's say in this case, the worst slowdown was about 2%. Here it's a little less than 5%. So in those cases, we would say, okay, if it's less than 5%, maybe you could even run this in production environments as well, okay, because it's not so much. So that was really surprising to us, actually. We didn't expect to see this. But then when we look at these other graphs, which are for MG and CG, then the overhead is really considerable, right? So it's almost 2.5 times slower, 4.5 times slower. So in those cases, we would say, well, maybe you don't want to run that in production, but it could still be very useful for testing and debugging, right? And in that sense, the slowdown is comparable to memory profilers in C, for instance. Okay, so maybe that would be a second use case. So how do I answer this question? Well, yeah, okay, performance, it's not too bad, could be better, but yeah, okay, yeah. So I don't have a better answer than that. Okay. Okay, I think this is all I wanted to say. I'm also running out of time, I suppose. So everything we developed is open source, so you can just access the source yourself. It's on GitHub, and I really want to mention also the other contributors to this project, which are Ruben Hamers, who's actually in the audience here as well, I believe, and Erik Horlings, who was another student who worked on this topic. We have a bunch of future work that I will not have time to go into right now, and finally, I'd like to just thank you very much for listening, and I'm happy to take questions.
Super interesting to see this, but I wonder, like, what's the application? So I don't expect my website will blow up because some channel was wrong, or I don't expect a spaceship will fall down. So So what's application?
Do you know of spaceships that run on Clojure? My own interest is actually not so much distributed applications, because core async is not meant for distributed programming. It's more for shared memory applications where you use channels as a programming abstraction to make the concurrency between the threads or the processes easier to manage. I think this was maybe, so I don't think that in this blog post by Rich Hickey, as he says this explicitly, but I think that it cannot be a coincidence that he invented this while at the same time Go, the Go language, was also gaining a lot in popularity, where this kind of concurrency model, channel-based concurrency, is also very popular. And so I think at the time the idea was that if you have these kinds of channel-based applications, then it would be simpler to reason about the correctness of your programs, right? Because it's supposedly like kind of a higher level abstraction on top of logs and shared memory and that stuff. But I think in recent years, also in the scientific literature, people have been studying, real-world GitHub projects in terms of, what kinds of concurrency bugs do we see in those projects. We also see that even if you have channels, right, you still have just as many deadlocks and these kinds of race conditions as when you program with logs, right? So it seems like maybe the nature of the kinds of mistakes that you make is a bit different, but it's still complicated.
What do you think will be the impact of this with relation to virtual threads?
So in principle, I think it's orthogonal to virtual threads, but I am very interested in virtual threads. So what I showed you that we support is the thread thing, the thread keyword from core async, but we do not support Go blocks. The reason we don't support Go blocks is because, well, the implementation of Go blocks inside of them is really kind of complicated, at least for us. So we don't support them. It would be very interesting, I think, if these Go blocks in core async would be replaced or supplemented with native support for green threads in the JVM. Yes, but then in principle it should just work. But yeah. Okay.
Hi.
Yes.
Very interesting. One thing that I noticed with all the examples is that it looks like all the examples of the mistakes have sort of dangling channels where there's nobody listening on a particular, or at least one channel where there's nobody listening.
Yes.
Is it possible to detect that? Or is it interesting to do that at all?
I think that you would need to add something as well, because I mean, channels, they are dangling until you use them, right? So in some cases you want to say, okay, this dangling is not so much of a problem because I promise you that later I will use it. And in some cases when you do not put this explicitly here, then you want to say, oh, but you have this dangling channel that nobody reads from, and so you need to check. So you would need to have a bit of extra information, I think, as well in the program. Yes.
Do you know why the second use case was so much worse in performance? Is there any reason that you know of that explains that?
And so it has to do with, let's say, the communication intensity of the programs. So let's say that the overhead that we impose is proportional to, well, the number of communications that the processes do. So the more the processes communicate, the heavier the overhead, or at least manifests itself in the figures that we see. So if you have an application where you have, let's say, very big computational tasks and only few message exchanges, then the overhead is, relatively speaking, low. But yeah, if you have a very short-lived task with a lot of interaction and synchronization between them, then you see it more pronounced, so to speak. Yes.
Thank you.
Thanks for the talk and the tool. It's a great tool, and I've had my share of correcting debugging after me, so it would have been more helpful if I had known about this. But it seems to me that a whole class of problems with creating correcting can be avoided if we could kind of offload the creating of processes and channels to some third party rather than having the processes create the channels themselves. So that like we could pass the topology to some function and have it correctly create all the processes and channels. Do you know anything about this, or?
Yes, well, something like this. So in the literature, it's called choreographic programming. Okay. And basically what they do there is you can think of it as, you know about sequence diagrams, right? So one way to think about these protocols is you draw the sequence diagram, and that's sort of simple for us to understand, and then you have the design, and then you want to implement it, okay? So what people are doing is they want to have a textual version of the sequence diagrams, right? And not just at the specification level, but also with, in which you can directly access all the data, right? So you have the communications with arrows, so to speak, but then also intertwined, you have if statements and while statements, and you can have all this kind of fancy control based on the data. And then what they do is they push a button, and they sort of decompose this whole sequence diagram into the separate lifelines of the thing, right? So you automatically parallelize, in some sense, your application based on this global view of the thing. And then by construction, so to speak, you do not get deadlocks, you do have this compliance thing. And that's, so that is what people in the scientific community actually are looking at, to do these kind of things. Yes?
Yeah, so you briefly touched upon Go loops versus thread. And one of the classes of bugs that I sometimes find is that the Go loops are scheduled on a thread pool of eight threads.
Yeah.
And then I end up, blocking on all the threads, and then I don't have Go loops anymore.
Yes.
Is that something that would change your approach in, is that something that we could, like if someone figures out how the Go loop works, could incorporate in your tool?
So I think this particular problem might have been easier between quotes to solve when you add, let's say, a deadlock detector inside the Go block somehow, right? Because they are scheduled by a separate thread pool, or in a separate thread pool, you have, well, as part of that, you can have a bit more bookkeeping information and keep track of that. And so basically count how many of the threads are waiting for something to happen, or and then do something to catch these deadlocks at runtime in that way. I think that would be, well, again, easier, but still kind of complicated than to incorporate it in this library that we have here, because what we have here is, let's say, a bit higher, right? So the closer you are to the actual threads, the easier it should be to do this kind of analysis, I think. Yes.
Thank you for the talk. Just wondering if you can instrument things like back pressure or thread starvation, other types of concurrent problems.
I think it's a very interesting problem, but I don't have a solution, because especially, well, things like starvation, you need to, I think you would need to know something about the scheduler as well, and that is not something that we consider at this level of abstraction, so to speak. So if we can get deeper into the scheduling mechanism, so to speak, then maybe yes, we can do something. But see, the thing that we wanted, so one of the design principles for this particular framework that we have here is that we wanted to change, as well, basically nothing in core async itself. We just built something on top of it without, going into the internals. And if you want to have more advanced scheduling issues, I think that you would need to go deeper. Yes. Thanks.